Okay, this is lecture 21, and we're going to start to talk in detail about precipitation. And when we talk about the precipitation, we're going to talk about a few things. We're going to talk about rainfall and formation and types. And then, of course, we have variability in that rainfall, how it falls in time and how it falls in space. And then we'll look at the aspects of disposal of the rainfall on the watershed. Where does it go? And how does its location where it goes change through time? And then at the very end, we'll set up design storms, which we're going to spend lecture 22 talking about. So if you look at precipitation and its formation, you typically have aerosols that are dispersed in the air that act as condensation nuclei. And so the moisture that's in the atmosphere condenses around this condensation nuclei. And if it gets heavy enough that you see it falling through the atmosphere as precipitation. One of the basic requirements of precipitation is lifting of the air mass. And if you have a mass of air, as it goes up in the atmosphere, it cools, and that cooling causes it to condense, and basically the droplets condense around the nuclei, and it falls as rainfall. So we have three different types of lifting. We've got this frontal lifting, which occurs when warm air is lifting over the top of cool air when a front passes. We've got orographic lifting, which happens when air rises up over a mountain range. And then we have convective lifting, which is what happens when you get heating and you get the air drawn up by convective action, such as in a thunderstorm cell. So this is an example slide here looking at frontal lifting. And so this is what you might see in terms of an air mass or a weather map, where you've got the various masses of air, where you've got cold front, warm front, back onto cold front. So, you see these triangles. That's the presence of a warm front, cold front moving. You got the cold front here, where the warmer air is moving. I'm sorry, I got these backwards. So you got the cold front moving through here. You've got the warm front moving this way. And so if we cut a cross section of that, we've got this cold front moving in, forcing that warmer air aloft. And that's where you get this kind of this real blunt edge to this frontal system. And this is where you get a rapid rise of the air mass, and that's where you get these thunderstorms and these big cloud formations that go 30, 40, 50, 60,000 feet into the air. Now, if I've got a warm front that's moving over the top of a cold front, which is, again, we're at this point in this graph is here, this point in the graph is here. And so if I get a warm front riding up over the top of a cold front or a cool front, it's a much more gradual process. And so that air, as it moves up, that's a smaller gradient. And so you don't get quite the massive thunderstorms. You get nice, typical day-long drizzle. Rain is common, whereas in this particular situation, you get a rapid dump of rain, because this is such a fast process of forming these thunderstorms. So if I look at orographic lifting, you can think of this in like the Sierra Nevada range or the Rocky Mountains. On the windward side, you get the air masses lifting up over the top of the orographic feature, and you get the rain falling out. And on the leeward side, it's much drier, and so you end up getting a deficit of rainfall on this side, because all the moisture has kind of been dumped out of the system. And you see that in the Cascade Range in the Pacific Northwest. On the west side of the Cascades, you've got Seattle and Portland and those areas, which are much wetter. And then on the eastern side, eastern Washington, eastern Oregon, those areas are much drier. They're almost desert-like in some respects. I mean, you get out into extreme eastern Washington State, into Idaho, and that part of the upper United States. It's a much drier environment there than you have west of the Cascades. If we look at atmospheric rivers, I think I've shown you this slide earlier. This is from a former USGS colleague, the graphic in a paper. He's now with the Scripps Institute of Oceanography out in California, in La Jolla. This is basically the state of California. See the Central Valley here wide is a typical kind of atmospheric river that just loaded with moisture. And as it comes in, you know, you get the coastal range, you'll get a orographic lifting here, but you get the massive amounts of rainfall dumping on top of the state of California. And the interesting thing is you look and you can get as much as 15 inches or more of rain during one of these storms. The last thing to talk about is the convective lifting, and that's basically you got to have the sun to give that source of heat. So you get this surface heating and re-radiation, and then you get this lifting of the air mass going up, and it condensates, and then you get this thunderstorm. So this is typically what you would see in summer afternoons where you've got a lot of humidity and moisture. You can get these pop-up thunderstorms. That's all due to convective lifting. So now as we move into rainfall variability, what we're talking about here is that rain is distributed in both space and time. And so how does that look? You know, what should we expect when we do these rainfall runoff studies? We'll have to kind of understand the mechanism of how we distribute our rainfall when we're doing like a design for flooding or stormwater detention basin. We're going to have to pick a rainfall value, so an overall magnitude of a rainstorm, and then we're going to have to distribute that in time. But you also have to think about, okay, how's that distributed in space? And so for most of our stuff, we're going to assume a uniform rainfall distribution in space for the most part, but that's not always true. So you need to understand kind of what the limitations of that assumption are. If we want to measure rainfall, we typically, this is three ways to measure rainfall. This is a typical Belfort rain gauge. The rain comes in the top of this thing, and it has a scale system here that's calibrated to the amount of rain that comes in. These are very accurate rain gauges. They're the kind of the standard that are used in studies by the National Weather Service or monitoring situations by the National Weather Service. I think the one at Stonehenge at the university's rain observation site for the Weather Service is a Belfort weighing rain gauge, and you have a bucket that sets in here that has to be dumped after every rainstorm because otherwise it fills up. The tipping bucket is what you're seeing in this graphic here. And basically, you've got a little teeter-totter mechanism. There's typically the outer shield is removed here, where you can see, but that outer shield basically shields all this internal mechanism. So it's similar to what you see on the top of this. Is what if you were just looking at it, you wouldn't know that there's this mechanism going in here. But you've got this funneling system that funnels the water that's coming in down on top of this teeter-totter. And this teeter-totter is calibrated to where it will tip at 1/100th of an inch of rain. And so there's a mechanism down here, either magnetic or some have an electric switch. And every time it tips, it's able to record that tip in the electronic data logger. And that's how we, you've got a time recording going on there, and that's how we get the rainfall. The one on the right is the old-fashioned thing you put up on the fence post, and many of you have probably used those or seen your parents or grandparents or some family member have these. And this is just a total catch rain gauge where you have to basically just dump it after every rainstorm if you want to keep track of the rain amounts. These are fairly accurate. They just don't give you any time distribution. These give a time distribution. Now, one thing I want to mention here is this definition of isohyets. That's what you have when you have contours of constant rainfall or equal rainfall. Now, you're used to topographic contours where you've got equal topography lines, the contour intervals, and you know, say if you get a topographic map, it's got some contour interval. That means the designation between two different lines is a jump by the interval. So if it's a 2-foot contour interval, if it's a 5-foot, 10-foot, 20-foot. So if we look at this next graph, this is from a study I did on the state of Illinois' 24-hour maximum rainfall happen event that was centered in and around Aurora, Illinois. And you can see here, this set the 1-day 24-hour rainstorm record, which was right here in Aurora at 16.91 inches. That's a lot of rain, and that caused a lot of flooding in this part of the state. That's why we did the study. You can actually look at the results of that study here at this URL. But look here, you've got lines of equal isohyet or equal rainfall. So there's a 14-inch line. Here's the 16-inch line. Here's the 12-inch line. And how did I build this? This was actually, I didn't build this. Was built by a fellow named Stan Shagnon over at the Illinois State Water Survey. But you can see that we've got observation points here where we had rain gauges. You see these lines here, are these points? And here's where we have observations. There was a rain gauge right there. There's a rain gauge right there. These are various rain gauges. And they used a methodology called kriging to basically come up with a map of equal lines of precipitation. So you can see where it's 12-inch, we get away from that Aurora center point there, and we get down to 10 inches. Here we're at, let's look for there's a 4-inch, 5-inch, 6-inch, 8-inch. Here's 10-inch. So there's a high point there. It almost looks like a contour from elevations, but it's not. But anyway, this is you'll see these maps that have isohyets of storm total rainfall. Sometimes it'll be annual rainfall, which is what we see here. This is an annual rainfall. So this right here is inches. These are in centimeters out here. This is in inches. So this is the 48-inch annual rainfall contour. Here is the 32-inch. Here you can see the 16-inch. And so we're sitting here in Rolla, which is squarely here. Our averaging, I haven't looked it up in a while since the new data in ensuing years, but it's typically around 38 inches of annual rainfall is what we typically get. You'll notice as we go farther west, it gets drier. And that's because of the way rainfall happens. It's the source of the rainfall. This is the Gulf of Mexico. And so this is a big source of moisture. And so as it moves north and then gets into those prevailing westerlies, the system kind of steers it this way. And so the farther north you are and the farther west, the drier it is. So you can see these are areas here. Look at this orographic effect. You got the Pacific over here, which is a huge source of precipitation. But you got the Cascade Range, and by the time it hits the Cascades, it dumps most of its rain out here in the northern or the western part, and then by the time it gets into eastern Washington, into the northern Rocky states and stuff, you get a much drier situation. It's just because of the proximity to the source of moisture and being on the leeward side of the mountains. So that's with respect to space in terms of rainfall variation. Now let's turn to rainfall variation with respect to time. And these are called hyetographs, which are rainfall, graphs of rainfall. And this is incremental rainfall in terms of intensity. We can also have incremental rainfall in terms of total precip or precip amount. Okay, so make sure that you know what you're looking at when you look, because both of them are called rainfall height-o-graphs. So this is time and this is intensity. Here it's in inches per hour. So you can see this is just over an inch per hour in that first hour, a little bit more in the second hour, about the same in the third hour. And then the fourth hour, it really steps up and then it falls off. And so these are different storms here. This is, again, another one in terms of intensity on this side, and you can kind of see the various types of rainfall. This is a cumulative rainfall height-o-graph at the bottom down here, where I've got the accumulative amount of rain. And so this January 8 storm, where this is a incremental intensity height-o-graph, when I take it down to the cumulative rainfall height-o-graph, you can see that we just keep accumulating the rainfall, and that shows you how that rainfall was accumulated in January 8th. This compares this storm with that. Here's July 24th. You can see what it looks like compared to the two. You can see the evidence of that rain at the end. It pops up here. And again, we're looking at a cumulative graph. This is a graph that, so that's about the time variation of rainfall. Let's talk about the disposal of rainfall. So let's kind of break this, this graph down. So on the x-axis, I've got time. On the y-axis, I've got rate relative to precipitation. So you can see that as the precipitation is occurring early on in the storm, you can see that we've got some of it, the majority of it, going into infiltration. And if it's raining hard enough, it's going to go off into surface storage and soil moisture storage. And we actually have to build up some filling of that soil moisture and the surface storage before we can ever start to contribute to the channel flow, the overland flow, the unsaturated flow, and the groundwater flow. It's got to fill those interstitial spaces in the soil mass throughout the unsaturated zone. The unsaturated zone being that area. So if this is the ground right here, and so rain is falling on this ground, at some point way down here, I've got some groundwater table that's saturated. And then I've got up here is my unsaturated zone. You'll hear it called the UZ zone, and that's easy for me to say. And essentially that's that zone here where this is normally, it will dry out, it will drop its water down into the groundwater table. If it stops raining after a time, it will dry out, and the interstitial spaces are open, and that's where we get our infiltration. And this is very difficult to model, and we're going to work on infiltration models to look at how water infiltrates into this unsaturated zone. But as you notice here, once we fill this up, then we start to be saturated through here, and then the water runs off. And so we end up getting in this overland flow and the channel flow, most of this water runs off down into the receiving streams. Okay, so last thing to cover here is talking about design storms. And we have to, at the end of the day, we're looking to design something. And so we have to design it against some risk or some probability of some event occurring. And we use what's called the intensity, duration, frequency relationships. We're going to come up with a value of intensity of a rainstorm or amount. We can intensity or amount of rain. We're going to have a duration, which is, how long does it take to get that amount of rain on the ground? And then we've got the frequency, which is, well, how often do you think this is going to occur? And that's where we get into things like the 1% annual exceedance probability, which is also known as the 100-year rainstorm, the 2% annual exceedance probability, also known as the 50-year, the 10%, which is also known as the 10-year, and there's the 0.2%, which is also known as the 500-year. Those are all have to do with the frequency of occurrence of this design storm. And so when we think about the frequency, we typically think of it, and you've heard it referred to most of the time in terms of return period, TR. And so that's when we use language like 100-year rain, or if it's flooding, 100-year flooding. But all a return period is really a probability measure. And so when we think about the probability of occurrence, that's simply 1 over TR. So if we've got 100-year rain, that's 1 over 100, or a probability of 0.01, or 1%. That's when we talk about the 1% annual exceedance probability. And we'll call it usually for short AEP. So if 6 inches is the 100-year rainstorm, that means there's a that location will experience a 2-hour rainstorm of 6 inches or greater. So again, the frequency or the intensity is basically in this sense going to be 6 inches. So it's an amount and not an intensity. So it's not a rate, it's an actual amount. The duration is what? 2 hours. And the frequency is 100-year, or 1%. We call these the IDF relationships, as I mentioned on this previous slide. So this is the IDF. That's where we get them. And we can get that value based on statistical analysis that's been done by the National Weather Service. And so they produced, and this is an old publication called TP40. We no longer use this. We've got updated statistics, but I want to show you this. I mean, there are still a few states that aren't in the new NOAA Atlas 14, which we'll talk about more in lecture 28, or I'm sorry, 22, but this is TP40. So you still might be consulting this. This is for durations of 30 minutes to 24 hours and from 1 to 100-year TRs. And so you can see here, if we look closely at this, we've got isohyets of this 100-year probability, 24-hour duration, and then we'll get the inches here. And so if you look at this, this is an 8-inch, 9, 10, 11, 12, 13. So here's the 13. Here's the 12 isohyet. Here's the 11. And you can see we're here in Phelps County in Missouri, which is right here. And let's erase that. So there's Phelps County. And so we're between, there's the 7. So here's the 7-inch, here's the 8-inch. So Phelps County, at least from the 1961 report by Hirschfield, which is called TP40, Technical Paper 40, we're somewhere probably around 7.5 inches if we were to use that information. Now, we're not going to use that, and if we're working in Missouri, we're not going to use TP40. We're going to go to something called NOAA Atlas 14 on the web, and that's going to be a point-and-click map exercise where we're going to come and click on Phelps County, and we're going to see exactly what the statistics are. Be interesting. So this is 7.5 inches. We'll have to do that in another lecture and see what that looks like in terms of what NOAA Atlas 14 says it was and what it was compared to what the 1961 publication. I'm sure they're going to be somewhat different. So in part 2 lecture, which is lecture 22, I'm going to talk more about the sources, you know, these IDF maps, where you get them. Most of the time you're going to go to NOAA Atlas 14. And if you've got some return periods that you need to have for some design that's not on NOAA Atlas 14 or one of the other Weather Service publications, you can actually interpolate. And then we'll speak about the hydrograph that we can generate from that. So when we go to NOAA Atlas 14, we're going to get an amount or a rate that's going to be the total for that duration, be it a 5-minute or an hour or 6 hours. But then we have to sometimes interpolate because it may not have the actual frequency that we're looking for. It, depends. So we've got, the 2-year, the 5-year, 10-year, 25-year, 50-year, et cetera. But let's say that for some odd reason, you might want something different, maybe a 28-year or a 15-year. I don't know why you would necessarily want that, but if you wanted to look at more things, you can actually interpolate to get the return period not included on those maps. And then we'll talk about getting a hyetograph of time distribution and the various rules or methodologies there are out there. And then lastly, we'll wrap up with talking about limiting storms. These are the things that would be the outer edge of what could possibly happen.